Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on scientific programming using Python. Now in this tutorial, I'll be explaining you guys how to integrate an ordinary differential equation using the some of the functions available in Python. Okay. Now, if you want to do if you want to integrate an ordinary differential equation, okay, there are functions that are available in SciPy library which does that option. Okay. Now let's look at this with a simple example. I won't say it's a simple example, but it's not much of a hard example either. Okay. Now this equation is actually a simple mass spring damper equation. Okay, if you guys do not know what mass spring damper is, it's simple. What you have is that you have a mass which is being suspended, which has a damper which controls. You have an object which has a mass m accelerating up and which is moving up and down. Okay, and because due to this motion, they call it a simple harmonic motion. Okay, there is a motion such that it has an acceleration. The mass actually opposes the acceleration, and the object has two components to it: a damper which opposes the velocity, which acts as a sponge to control the velocity, and then you also have a stiffness given by a spring. Okay, you just attach a spring, and then the object becomes harder to move. Okay. To explain what's going on over here, let me explain this in a simple figurative diagram. Okay, imagine you have a layer and you just have imagine you have a mass m. Okay, this mass m is somehow connected to some kind of a suspension. Let's say. For example, let's say imagine a two-wheeler, your car, or a two-wheeler, or a bike, car, everything. This mass is actually the object, and this gives actually a suspension. Okay. Now, the suspension has a damping coefficient c, and this suspension has a spring retarding mechanism as well, which kind of makes it go up and down. Okay, up and down, which whose stiffness can be given by term k. Now by Newton's law, Newton's second law. What I'm trying to say here is that, okay, now if your mass times your acceleration. Okay, let's say your up and down motion is x. Okay, now if your object is continuously moving, then your mass times acceleration is actually a force. Your mass opposes acceleration by giving it a counteractive force. Okay, your damper will oppose the velocity by giving a counteractive force, and then your spring with the stiffness k will oppose your displacement by offering a force kx. Okay, and now in a normal oscillation, okay, or unforced oscillation, the summation of all these forces at any instant is 0. So what happens is that if the acceleration tends to pick up, the damping will increase, or the acceleration tends to pick up. Okay, your damping and the velocity and displacement will adjust accordingly, so that the force balance is common. Okay, now this is about natural displacement. Now what we are going to say is that we are going to look at force displacement or force vibration. I'm just saying that this entire object is acted by force which varies by notation f naught sine omega t. Okay, so instead of an object being static, what I'm saying is that then the object has an undulation like this, going up and down. For instance, you can imagine a car going on an undulated road like this. Okay, for instance, it's like this: a mass, okay, a suspension, a spring, okay, and you have an undulated road like this, and your object is going like this, and this external undulation, let's say if you are able to make let's say if you're able to give it a function like this, like f naught sin omega t. I mean, it's not practically possible to have an undulation which is, I mean, it's not ideally possible. Let's say you have some external disturbance like this, and as this object moves this direction, the up and down vibration, okay, is actually x. Okay, and if you want to model this kind of an equation, okay, if you want to model this kind of equation, find the displacement, displacement, acceleration, and the velocity at each and every point. It's possible to do that. How? Using this option over here. Let me explain what's going on. Okay, now this is the main governing equation, and since you have acceleration and velocity, when you want to solve it, you need to give the initial displacement, and you have to give an initial displacement. Okay, the displacement of the object at the time t equals 0, and then you have to give dimension to the function that there's a velocity at time t equals 0, or else you have to give another value of displacement at t at some other time. Either way, you have to give one of them. You have to give two initial conditions to solve this problem. Okay, how are you going to model this? Is simple. Keep the acceleration with the highest degree on the left hand side, and push everything to the left hand side. So you'll get an equation like, if you do this, you get an equation like x acceleration as f naught sin omega t divided by mass minus c by m of x dot, c by m of acceleration, and then c by m of velocity minus k by m of x. Okay, and to solve it, what we need is that the procedure is that we need a function that represents the equation and derivatives first, and then we need a ODE int function from SciPy, and then some initial conditions to be plugged in. And let's see how this is done. Okay, this is the entire function. So let me copy all this. And let me create a new file over here, paste it over here. Let me save this with the name ODE solve 1. Okay, let me explain what's going on. Now numpy, and now from SciPy.integrate, I need this function called as ODE int for integrating the ordinary differential equation. I need this is matplotlib. Okay, now this is the damping function. Okay, I set the force, I set omega, I set mass, the damping, and stiffness like this, and so that's about it. I set the values over here, and then this damping function has two variables, x and t. Okay, x and t. Now what I'm going to do is that I'm going to set x naught to be x of 0 and x1 to be x of 1. Now x naught will be our displacement and x1 will be our velocity. So what I'm passing here is that when I pass x, I'm passing x as a list or a tuple with two values. One value for the first value for the initial displacement, and the second value for the velocity. Now, and then what I'm going to do, I'm going to set x2 to be the function which we get. So this is your initial displacement, initial velocity, and then this is acceleration. So how does this function work is that, okay, now how does this function work is that for the first time step, okay, it's going to calculate velocity, and it's going to get the velocity, acceleration, and everything, velocity and displacement, and it's going to calculate the acceleration, and then it's going to return both of them. It's going to return velocity and displacement, velocity and acceleration. So it's going to return velocity and acceleration. Okay, now how do we do about with it? These are just a repetition of the same. I'm going to set this init is actually the initial condition, 0 initial velocity and 0 initial displacement and 0 initial velocity. Okay, and then I set the time to be 10 seconds. I set the time to be 10 seconds between 0 to 10. Okay, with 101 points between, and this is the magic line. This is the vital part. ODE int should have 3 arguments: dampfunc, int, and t. This dampfunc is actually the damping function which we used. Okay, init is initial condition which is given over here, and t is the variable with which the integration has to be. The ODE has to be integrated and solved. That's about it. And then nothing much. I'm just getting mass over here, but doesn't matter. I'm just calculating the acceleration separately using the same function, and then I'm plotting. And then if I do all this, okay, what will I have is that I'll have x. Okay, this function is going to return me 2 values. X will have 2 values. The first value will be my displacement, whereas the second value will be my velocity, and and that's it. So initially it takes displacement and velocity as the initial condition, and it's going to return me this function is going to calculate the acceleration and everything, and then it's going to solve. ODINT is going to integrate out velocity and displacement out, and it's going to return that and keep it in x. That's what it's going to do over here. So now this line will plot the displacement, this will plot the velocity, this will plot the acceleration, setting the axis, takes, legends, okay, and frame alpha to be 0.5, so that the frame is translucent, and everything, and nothing much. So if I were to run this, there you have it. Now your x is actually your sinusoidal function, your initial displacement, okay, which is a blue line. Your red curve is actually your velocity, and your green curve is nothing but your acceleration. Don't worry about the units. Each of them have their own separate units. These are just magnitudes plotted out, so that's about it. And if you want to experiment all this stuff, you can just change the values over here in the function values over here, and like that. And if you have any ordinary differential equation, it doesn't matter, just plug them in, it'll work out fine. Okay, not bad, huh? And similarly, you have another example. This time I'm going to raise the stakes up. I'm going to do a little more of a complicated example. This is, if some of you guys might not have heard about it, but this equation set is actually called as the Lorenz Equation Set. Okay, now what's the specialty of this is that, okay, now this is that, like, if you solve this equation with lambda to be 10, with sigma to be 10, rho to be 28, and beta that we use over here to be 8/3, with some leave this initial condition. If you saw this equation set is actually chaotic in nature, and if you guys don't understand what it means, okay, if you guys want to know more in detail about what's going on, just type Lorenz Butterfly, okay, and if you just look at Lorenz system, okay, he'll explain this very clearly. What they say is that it's a Lorenz system actually is a system of ordinary differential equation, okay, given by Edward Lorenz. It say that the solution is chaotic, meaning you can never for a particular set of values, you cannot predict as to what will be the next set of what will be the next time instant value is. Like for example, look at this. image over here. Hopefully this loads. If you look at it, if you look at the trajectory of this particle, okay, and if you don't analytically solve it, you just don't know, you have no idea as to where it will move. See, this particle is moving like this up, and if you look at this particle over here, just moving up and down like this, and all of a sudden it just moves to the other lobe. And then just like that, after some time, without any further cause or any explanation, it just moves to the other lobe. It's like you don't have any kind of predictability as to how it will move. Just solve this equation analytically, even then you won't get an answer, but solve this by numerical methods, you're able to get a solution. But this is how it is. And if you look at this plot over here, okay, if you look at the picture over here, it kind of looks like the two wings of a butterfly, with a butterfly body in the front, and these two are wings. So sometimes they call it as Lorenz Butterfly. Okay, not bad, huh? So that's what we're going to solve today. Now this Lorenz equation for this set of value, sigma equals 10, rho equals 28, and beta equals 8/3, this Lorenz equation solution becomes chaotic. Okay, now let's see how to solve it. Okay, what we need is that for this equation, since all of these equations are just first derivatives, we need three initial conditions: one condition for x, one condition for y, one condition for z, and all these three initial conditions are actually displacements. So our function requires these three equations. Our function requires these three. Where did I keep? Come on. Yeah. So our function, Lorenz function, requires these three constants. Not a problem. It requires three inputs. I'm giving the inputs to be st with the name st. St of 0 is x. St of 0 is actually an initial x displacement. St of 1 is actually an initial y displacement, and St of 2 is actually an initial z displacement. Okay, and I give them to x naught, y naught, and z naught, and then I use the Lorenz equations over here to solve them. Okay, and I'm going to return the the velocity in x, y, and z. Okay, and then I'm starting with the initial condition for x equals 2, y equals 3, and z equals 4. Okay, and then I'm setting the time period to be between 0 to 60 seconds with the time step of 0.01. Why such a slow point? Because if we give a very last time step, then we might not the figure may not come nicely. That's the reason, nothing much. Okay, and this is the main line. I'm getting all the states. I'm getting all the solutions of displacements of x, y, and z from ODE and t by passing the Lorenz function, the initial condition within it, and the time t. And then I'm just extracting x, y, and z. The displacement x, y, and z from the states which we got over here, and then I'm going to plot this in 3D. Don't worry, I just explained. MPL_toolkits is actually matplotlib toolkits. Okay, there's an option called as mplot3d, which actually makes 3D plots. Okay, from that I'm extracting axis 3D. Okay, not much, but okay, what I'm going to do is that I'm just going to make this figure. I'm going to get the axis out of this figure and making it a 3-dimensional projection, and I'm going to I'm going to plot them like this. This line sets the x label, y label, z label, legend. This is going to say the figure. This is going to just plot the value z, plot the values x, y, and z. Okay, and it's going to connect all of them with red lines. Simple as that. Okay, now let's run this up. So if I were to copy all of this, now let me write a new line. Control S, ODE solve 2, save it, run this. Check this out. It's going to take some time, but fine. Look at it. Now this is actually a Lorenz butterfly, and now this is actually a three-dimensional movement of the particles. So if you look at it, this plot itself is 3D. So I can move up and down to see that whatever direction I look at, you see this peculiarity feature. This is because of chaos. You see, only a particular region of space is being occupied, whereas you can't within a particular region within a particular region. Okay, the path of the path of the particle is locked, but still it becomes unpredictable. Then that's the beauty of Lorenz equation. The Lorenz equation system is actually chaotic in nature. That's the reason why you get a plot like this. Okay, so if you guys want to know more about it, you can just read it up. It's not very hard, and it's very simple. So it's not very hard, so it's easy to look at. So not a problem. So it won't be a big problem. Okay. That's about it. That's about the Lorenz equation. The next tutorial we'll see something about how to do FFT and fast Fourier transform and inverse fast Fourier transform with the SciPy modules. That's all I have for you guys in this tutorial. Thank you guys for watching, and I'll see you guys next time.